So 5.2 is about the rate law. To me, this is one of the easier ones. I don't know what you guys are gonna think, but anyway, okay. So from now onwards, every time we're gonna come across a reaction, we're not just gonna see an arrow going from the reactants to the products, but also an arrow that's from the products directed towards the reactants. So there is a word that we need to be familiar with, just be familiar with, not get into the details of it. And you may have heard of it. It's equilibrium. We use it we use it to describe things even when it's not about chemistry, but we'll stick to what it really stands for in science. So whenever there is reactants making products, there's always going to be the products breaking down back into reactants, decomposing back into reactants. And this is how it happens in nature. There reaches a point when the reactants are going to be making the products in a certain concentration, and the products are also going to be making the reactants back again in a certain concentration. So when that concentration has become constant, it's no longer changing, we say that the system is in equilibrium. Think of a closed system, all right? Because equilibrium can only happen in a closed system. You have water that's evaporating, like in this image over here. You have water evaporating, but you're not letting it escape. So what's going to happen is that some of the water molecules are going to go back into the liquid form. I understand that this is an example of a physical change, but it's pretty much the same idea. So let's look at an example that's more about a reaction. So in this reaction over here, you have N2O4 and it's converting into NO2. Now, because this is a closed system, there is going to be eventually, gradually, there's going to be a time when the NO2 is also starting to turn back into N2O4, and this is what these arrows represent. So even though there are a lot of scenarios where equilibrium can happen, so there are a lot of things that have to be there. For example, the temperature shouldn't be changing for you to achieve equilibrium. But until like we're in this section, it's enough to know that equilibrium is just meaning that the forward reaction is equal to the reverse reaction. Remember that this does not mean that whatever concentration you have of the reactants is equal to the concentration of your products. This is not what it means. What this means, now this is the key part that you have to remember. What equilibrium means is that whatever concentration you have of the reactants and whatever concentration you have of the products, it's no longer changing. Okay, so with the square brackets, again, the values are not changing, the molarity is not changing, and once they're constant, that is when equilibrium has occurred. Okay, let's go to the next slide. Rate law, also known as differential rate law, is simply you determining what is happening to the product concentration if you are changing the product concentration of your reactants. So there is a formula for this that you'd be using in order to mathematically figure it out. And it states, it doesn't state, this is the equation. Rate law is equal to K, which is a constant. We'd be able to mathematically figure this out once you have information about the other things in this equation, and you have the concentration of your first reactant and you have the concentration of your second reactant, and it's raised to the power of 1 or 2. It also can be raised to the power of 3, which is called the third order reaction, but we're never asked about that. Okay. So the first order reaction means that if you were doubling up the concentration of a reactant and it was also doubling up the concentration of your product, as in you were able to yield double the amount of product than you initially were, then it means it's a first order reactant, and you would write a exponent of 1. So here you would have written a 1. If you doubled up the concentration of a reactant and you notice that you quadrupled the concentration of your product, then that means it's a second order reactant. And you would write a 2 as an exponent. Third order reaction, which is irrelevant to us, but I don't know why I wrote it here last year. If you tripled up the reactant concentration and it also tripled up the concentration of your product, then it's a third order reaction, but we never have to do this. And then you have the 0th order reaction. This is something that concerns us. It simply says that if you doubled up the concentration of a reactant and it didn't bring about any change in your product concentration, then it's a 0th order reaction. An overall order means that once you have figured out the exponents of each of your reactants, you combine them, and whatever number you get is the overall order of the reaction. Here I have a reaction in which NO is reacting with chlorine in order to yield this NaCl. And I want to figure out the reaction order for NO, and I want to do that for chlorine also. I have to do that in order to figure out the rate law. Now, in order for me to check NO, I want to go for things or trials or runs, whatever it's being called in there. I want to go for the one in which the NO is changing. But because I currently only want to decide for NO, I'm not going to be looking for a concentration of chlorine that's also changing. I want that to be constant. So in trial 1 and trial 2, I noticed that I did double up the concentration for NO, but the Cl2, the chlorine, is constant. Okay, so in trial 1 and 2, I noticed that when I doubled up the concentration of NO, the rate at which I was producing NaCl, it has not just doubled up, but it has quadrupled up. Okay, if it had just doubled up, I'd have seen something like 2.4 or something, but that's not what I'm seeing. So now I'm sure that because it's quadrupled, it's a second order reaction. Now let's look at the reaction order for chlorine. Now I want to look at the trials or experiments or the data in which my NO is constant, but my chlorine is changing. So I cannot take 2 and 3 because even though the chlorine is doubling up, the NO is changing also, so I don't want to go for that. I am going to have to go trial 1 and 3, and I noticed that when I doubled up the concentration of chlorine, it doubled up the concentration, doubled up the rate of the product that I was yielding. So I know that this is a first order reaction. Now let's look at how I've written it. My rate, the K constant, which has to be there every time we write the rate law. And then I write NO2, the square brackets mean concentration raised to the power of 2, and chlorine, again, square brackets raised to the power of 1. And when I combine 2 and 1, I get this, that it's an overall third order reaction. So what if you wanted to do it mathematically and not just depend on your judgment? So I would insist that we always use this method. What I did is that I took the rate and I just wrote the rate law as it is. Rate is equal to K, square brackets NO. And because I'm trying to figure out the order, I have written an X over here. That's an exponent I'm trying to figure out. And then for chlorine, I am going to write a Y or an N, whatever. And then I'm going to put in the values for that. Okay. And for the values, I'm going to first figured it out for NO. So I'm using trial 1 and 2, and I'm just writing the rate from the rate column, and then I'm letting the K as it is because I haven't figured that out yet. And for NO, I'm going to write the concentration for NO, which is 0.400, and my exponent just the way it is. And then for CL, which is 0.200, and then the Y. And then I'm going to divide that with my trial 1. These are the trials that I chose to figure out NO's entire equation. And then I divided that by trial 1, 1.2 times 10 to the power of -6 is equal to K and all that. Now I'm canceling out all of the things that can be canceled out. I don't have a scientific calculator, so I just divided the Mantissa as 4.8 divided by 1.2, and both the powers get canceled out. So I get a 4 for that part of the equation. And then when I divide 0.400 by 0.200, I get a 2, and it has an exponent of x. So I know that my x has a value of 2. This is how I figured it out for NO. Then I'm gonna do the same math for chlorine. This time I'm gonna be using the chlorine's rate, and I'm gonna be dividing it. And once I'm done, I'd be able to get a number 1. The good news about these equations is that every time you're gonna divide the rate, the trials, you'll always get whole numbers. So what if you wanted to do it mathematically and not just depend on your judgment? So I would insist that we always use this method. What I did is that I took the rate and I just wrote the rate law as it is. Rate is equal to K, square brackets, NO. And because I'm trying to figure out the order, I have written an X over here. That's an exponent I'm trying to figure out. And then for chlorine, I am going to write a Y or an N, whatever. And then I'm going to put in the problem that is just written as a question on the previous slide. So please try to do this like this first, and then you can check the answers. Hopefully, there's not going to be a lot of problems when you're trying to figure out for the answer for part A. For part B, you have to figure out the value of K. Now, you have the rate, which is this column, and you have the concentration for NO2, which is over here, and you have the concentration for oxygen also. So I just picked up the first row, and that's why I've written all of the values according to that. Part C is asking you to figure out the units. Now, like other problems that we've come across yet, there are no fixed units for the rate order. It depends on the units that have been given to you in the table, in the graph. So the easiest way to figure this out is to simply replace the units in your equation. Notice how in 8.52 times 10 to the power of -2, this was the unit. So I wrote that over here, and then this slash means divide. For NO, it was moles per liter, and for oxygen is also moles per liter. So I simply put them over here. I canceled out the ones that I could have canceled out, and if I couldn't have canceled out, I just
if they were multiplying, I wrote a -2 for that.